Let's talk about crypto AI agents. These agents have been the most hyped technologies over the past years, and for a good reason. They hold a lot of promise when it comes to automating tasks in way that we've never seen before. But there are also some real challenges. So first, most AI agents, they run in a Web 2 environment, which often requires them to give you direct access to private keys, which is inherently insecure and introduces a major risk when dealing with sensitive operations like managing your funds, right? And second, once an AI agent is deployed, it can be difficult to monitor and manage. So unless you have built some kind of dedicated UI or other management tool, you might find yourself having to manually access some server just to configure or control the agent. So in this video, I will be showing you a project that tackles both these issues. Use this project as a starter template for developing and exploring your own crypto AI agents. It is a demo plugin for the Eliza AI agent framework that enables a conversational AI agent to interact with an Ethereum wallet deployed on the Internet Computer, ICP. The wallet imposes security rules on the agent, such as setting the maximum transaction amount and enforcing a cooldown period between transactions. So why would we want to deploy an Ethereum wallet on ICP? It is because it comes with several advantages. So first, it enables us to use threshold signatures, allowing transactions to be securely signed without exposing private keys to anyone. Threshold signatures are a cryptographic technique offered by ICP that allows multiple parties to jointly sign a transaction without revealing their private keys. In simple terms, this means that smart contracts and ICP can sign transactions on more than 20 different blockchains, including Ethereum. The second big benefit is that the wallet is always online and that it can self-host its UI, its own UI, making it easy to monitor and control the agent. And this video is not a detailed tutorial on how to build Eliza agents or how to deploy Ethereum wallets on the Internet Computer. Instead, it's a high-level overview of the project and its components. So if you're interested in learning the juicy details, I have shared links to the project repositories in the description below. Let's begin by looking at the wallet UI that we deploy on the Internet Computer. The wallet UI is a simple web application that allows users to view the wallet's balance, its address, and ICP identity. It also provides a way to set security rules for the AI agent. And this is something that is really important here, setting these security rules. But by deploying the wallet to ICP, we can run the wallet in a more secure sandbox, if you will, and make sure that the agent doesn't run amok and do whatever it wants with your funds. Before deploying the wallet, let's briefly have a look at the code base and its various components. Let's open it up. The project consists of four main components. We have the backend, and that is the actual Ethereum wallet that creates transactions and stores data. We have the EVM RPC canister that is responsible for routing requests from the Internet Computer to an EVM RPC provider outside of ICP. We have the front-end canister, which hosts the actual wallet UI and makes it accessible through like a regular web interface. And finally, we have the Internet Identity, which is an Internet Computer component that allows users to authenticate with the wallet. And okay, let's deploy this project. So first, we need to start a clean copy of the Internet Computer replica. And once that is done, we can deploy the project and access the front end using the URL printed in the terminal. So deploying, building and deploying. Let's see here. Okay, deployment successful, and as you can see here, the URLs to all these 4 different ICP components are displayed or printed out into the terminal. So the web interface is hosted by the front-end canister, and to access the wallet using this interface, the user must authenticate using internet identity. And internet identity is the default identity provider for the internet computer. It offers an authentication using fingerprint, etc. So let's create a new identity here. Create passkey. And this flow is somewhat simplified when we are running it locally, so no fingerprint needed, etc. Okay, saved, continue. And waiting here. Boom. Yeah. So what you see here is that now we have an Ethereum address, and this Ethereum address is based on the internet identity we just created. We use the identity as the seed when derivating an Ethereum address. And we can also, in this wallet UI, we can receive funds. So we can scan the QR code, or we can just copy paste the address. And we can, of course, also send funds to an address using any amount. And then one important thing to point out here, one key distinction between this just being a regular sort of on-chain online wallet and this agent-enabled wallet is that we include this allow agent feature. And by clicking this option, the user can paste an agent principal, and that is the internet computer identifier. And once an agent principal is added, this agent gains permissions to control the wallet. Okay, at this stage, the actual agent has not been deployed yet, so let's proceed to do that. Well, navigate to the Eliza wallet agent repository. And before starting up this agent, I would like to show you just a few things that we have included in this repository. So this whole thing is based on the Eliza agent starter repository provided by the Eliza project. If you want to create your own Eliza agent, you can use either this repository or the original one as a starting point, and just fork it and add your custom agent functionalities. So within the source folder here, we have added the ETH wallet folder, which is the plugin that I've created. And this an Eliza agent is modular and consists of stuff like actions and providers. And in our case, I have added 4 actions that we can use when interacting with the agent. And those are getting the address, which gets the Ethereum address. This wallet, this agent manages getting the balance, gets the Ethereum balance for that address. Get identity, which means getting the internet computer identity, and this we will need later. And also finally sending Ethereum, of course. And I also wanted to show you the actual wallet provider. And this wallet provider is responsible for managing the internet identity, and it's also responsible for managing the communication with the wallet deployed on the internet computer. Let's have a look at the anatomy of the ETH wallet plugin. So the ETH wallet uses the plugin type from the main Eliza OS library. We have defined a name and a description, and of course we connected the provider that I just showed you, and also we configure it with the 4 different actions that we built. We will look more into detail at the send ETH action, since it's the most complex one. It's most interesting to look at. Unlike the other actions we have built, the send ETH action requires some parameters. Creating an action means implementing the action interface, and then giving the action a name. You give it a description for the framework to be able to use it. And then you define the handler. And in the handler method, that is where the actual work takes place. So what we do here is that we create an instance of the wallet provider to enable communication with the internet computer. And then we want to parse the message from the user and turn it into a structured data so that we can pass it on to the wallet. We are using the compose context and generate object functions of the Eliza frameworks to properly structure the request. The compose context takes some parameters, a template, and instructions on how to parse that template. Basically, what it does is this send ETH template it transforms the prompt given by the user or the chat message. It transforms it to the structured data we need to be able to interact with the wallet canister. So, for instance, we tell the AI only to extract the numeric value from the instruction, and we tell it to convert ETH into Wei, because the API endpoint in our smart contract canister requires Wei. And we give it some instructions about how the recipient address needs to be formed, like a fully qualified Ethereum address, etc. And once we have the structured input as a JSON, we can do some basic validations of these inputs before sending it to the canister. Finally, we get the ICP actor, which manages the interaction with the canister. Finally, we call the send ETH function of the canister and hopefully gets a successful response back. So let's start this agent up. Before deploying the agent, we must install all the dependencies. I believe that I may have already done that. Yeah. So, and then we will use this included start script to start up the agent. Let's see here. Okay, let's ask the agent to look up my Ethereum address. So calling agent has not been linked to a wallet, which is totally expected since we have not yet linked this agent to our ICP wallet. And to resolve that, we need to retrieve the internet identity principal of the agent. Let's see here. There it is. 05 blah blah blah. And we'll to take this internet identity principal and return to the wallet UI. We will paste it into the allowed agent principal field. And once this is saved, now we have given the agent permission to interact with this wallet. So now when asking the Ethereum address again, then we hopefully should get a successful response. And yes, we do. Now the agent returns our Ethereum wallet. So the next step would be to try to perform a transaction. And before making a transaction, the wallet needs to have some funds. So off camera, I added some Sepolia ETH to the wallet, and now we can proceed and try to initiate a transaction. And to make things easy for us, we will use the Ethereum address of the wallet as the recipient. So basically, we will be sending ETH from the wallet to the wallet. So send some ETH, like 0.0.1 ETH to the wallet address, and let's see how that goes. receiving response, and no agent rule set. It says action denied by default, and this, of course, is also expected because we have connected the agent to the wallet, but we have not yet defined any rules that permits any transactions. So to fix this, we'll go back to the wallet UI and access this small cogwheel here, where I have defined just two simple rules. So one of them being the wait time between transactions, and the other one is the max transaction amount. And let's say set the wait time between transactions to 5 minutes, and we will set the maximum transaction amount to some fairly big number to ensure that we that our transaction will go through. So saving the settings. With these rules in place, let's retry this transaction. Okay, send some ETH again. Let's see. And yay! Successfully sent some ETH. Nice. To verify that, let's head over to the wallet UI again and access the history tab to make sure that everything went well. So let's see. Yeah, and there you can see you have the initial top-up transaction where I added some Sepolia ETH, and then you can see that the ETH that we sent using the agent interaction. So this is all I had for you today. In this video, I have shown you how to deploy an Ethereum wallet with a UI on the internet computer. I've shown you how to grant an Eliza agent permissions to interact with this wallet. We have looked at how we can define these security rules to control agent permissions. And we have performed and verified a successful Ethereum transfer using this conversational agent. And while maintaining a wallet with the help of a chat agent might not be the ideal use case, the main goal of this demo was to illustrate this pattern of integrating agents with ICP wallets. For real-world applications such as automated portfolio management or token trading or Solana, you would most likely want to use some kind of custom trade AI agent instead. Thanks for watching. Let me know in the comments what other ICP demos and tutorials you would like to see. I'm particularly interested in cross-chain use cases, but any ICP features are fair game. See ya.